I'm Karl. I've done a bit of .NET and stuff in the past, distributed system stuff. But in terms of projects that I've done that are not work-related, that may be of interest to this audience, I did something called Fez, which is an F# to Core Erlang compiler. So you can compile a reasonable subset of F# to Core Erlang and run it on the Beam. So if you're interested in that kind of thing, check it out. I've got a Twitter handle that you're very free and welcome to use as you see fit. I work for Pivotal. I'm on the RabbitMQ core team there. Pivotal are very invested in RabbitMQ. They sponsor the development, provide it as part of their Cloud Foundry platform, and support as well. So this talk is really like a version 2 or a sequel of a talk I did at CodeBEAM Lite Berlin last year, where I kind of showed the RA library, showed how it behaves when nodes are killed, try to get a little bit of a feel for how it works in the real world. But with a very simple example. This talk is not going to do that. I'm not going to do a demo like that. This talk is more going to be about writing something a little bit more interesting using the RA library, or maybe possibly more useful. So RA is a Raft implementation, and we made it for RabbitMQ, but it's a separate standalone library. RabbitMQ consumes it as an external dependency, so it's completely decoupled from Rabbit itself. So RA, by virtue of being a Raft implementation, allows us to implement persistent, replicated state machines. And that's how it's useful. And when I talk about a state machine, I don't necessarily mean like a small number of fixed state type of genstatum, genFSM type of state machine. I'm thinking about a slightly more abstract example of having some input in form of a command and some current state, and then run some logic over that to return a new state. So it's like a state transformation in the simplest sense. And we'll be talking a lot about this apply function here that you kind of see in a simplified form here. We've been working on RA for a long time, actually. It's 0.94 on Hex PM. We pushed that this week. Doesn't really tell you anything, but it's just numbers. But in terms of its API, the API that you'll be using if you want to try it out, and the behavior you need to implement, they're pretty stable and won't change unless there's a very, very good reason for them to do so. So it's going to be used inside RabbitMQ. So it's going to be included in RabbitMQ 3.8. So there's a new queue type in Rabbit called the quorum queue, which uses RA to implement a replicated persistent queue. So for people that might want to be interested in using this library, this is a very good thing, because maturing consensus implementation is very, very hard. It takes a lot of time. It takes a lot of testing and application. And having it battle tested inside a very widely deployed open source broker can only be a good thing, worthy of several emojis. Right. So I do appreciate that not everyone will be familiar with Raft or how it works, and it's probably like enough of a topic for an entire talk. But I'm going to try to cover it in a couple of minutes, and so that at least people who are not familiar with it will have some view of parts of it. So Raft is a consensus algorithm. And when we talk about consensus algorithms, usually they're described as something that allows you to, in a cluster of processes, to agree on a value. But for Raft, I think it's more helpful to just think of it as an ordered log of commands instead, that all the members of this cluster will agree upon and agree on the order and the commands that are in them. So each in Ra, each member of a cluster is a process, and it has like a kind of like some kind of anatomy in terms of what's in the process, or what has it got logically has it got access to. So it's got a log. This is a log that we agree on. It's an index log of entries. It's on disk. It's got a configuration, so it knows about the other members in the cluster, so it knows who to talk to, which is very useful. It got some kind of pluggable apply fun state machine transition logic. Like that, this is what we're going to do today. We're going to write this logic for various kinds of state machines. And it's got the current state of the state machine. This is an in-memory bit of data that it passes to each invocation of the apply fun, along with the entry that comes from the log. And it's got something called a commit index, which is the index into the log where each member or server knows that knows it's been replicated to enough members to achieve consensus, and it's safe to read the log up until that state and pass those entries onto the state machine and make the state machine transition. So it uses log replication. Raft got a strong leader model, so it's got a leader that stays leader for a long time unless it fails or get disconnected or something like that. And it's got none or more followers. And when you want to change the state machine, you send a command to the leader. The leader appends it to his logs. It sends it to all his followers, or at least it tries to. And if it gets responses back to say that the follower has also written that entry to their log, and once you got more than half, so a strict quorum of those replies back, the leader knows that that entry is now safe, and it can increment the commit index and tell the others. So in this instance, we got a red line for one of the followers, and we know red lines are bad in the distributed systems. It means that that follower is disconnected or unavailable, or something is happening, slow, stuck, doesn't matter. But we can make progress still, because we have more than half the cluster is available and responding, so the leader and one of the followers. So that's okay. Eventually that follower will receive the entries that it didn't see at the time. There's a protocol for that, and it will catch up once it's made available again. So an important point is that every server in a Raft cluster will end up calculating exactly the same state machine state eventually. So they all run the same logic. That's the kind of the replicated state machine bit. So Raft provides linearizable storage, so effectively an order set of invocation that's globally ordered. And this is the foundation for many of the distributed tools that you might need in a distributed system, like log servers. It provides replication, persistence, so we can have data safety. We can have the log is on multiple nodes, and it can be recovered from disk if a process crashes. We have fault tolerance or high availability, so a follower can crash, like we saw in the previous example. That could be a crashed follower or an available follower, without affecting availability of the cluster to process commands up to a point. Obviously, this point is the strict quorum. And it provides a leader election process for when the leader crashes and there's no leader, so someone needs to take over. One of the followers will hold an election, and the one with the freshest log will be elected leader. And this is safe in terms of you won't lose any committed commands at this point. Ra also provides dynamic membership changes, so you can change the configuration of the cluster as the cluster is running. And ultimately, the idea is that it provides Raft as a library for people to use. There are resources that you can check out about Raft. If you check out the slides, they should be available. How do we use Ra? So in order to write your own state machine, you need to implement the Ra machine behavior, which I guess isn't unusual thing to API to have. So there's two required callbacks in the Ra machine. It's init1, which creates the initial state of the state machine, so the state machine as it is before any entries have been committed and applied to it, and any state transition has happened. And apply3, which is the function that we've seen before with an extra argument, which we will cover. which allows you to apply a command to the state machine and return a new state. So there's a few rules about the apply function. It needs to be deterministic. So every time you run it, if you run the same commands over it, it needs to return exactly the same state. So effectively that means no side effects inside apply 3. You can't throw exception or read from ETS or DTS or create Erlang references. They are different, right? Every time you create them. So you can't create them inside. You have to pass them in as part of the command. You shouldn't do things like send messages or write to disk or anything like that. It's effectively a pure function. And if you recall, every member will calculate exactly the same state. So if you send a message inside a 3-node Raft cluster apply function, you will send 3 messages, which is probably not what you intended to do. So Ra provides a way to control the side effects that you want to have in the environment, and we're going to cover that. Start a cluster, relatively simple. There's a fairly simple API for that to provide the members you want the cluster to have. All Ra servers are always locally named processes, and in the cluster they're always referred to by the name, the locally registered name, and the node they're running on. If you want to interact with the Ra cluster, there's a few bits of API for that. The first one is the process command, which allows you to synchronously process a command against a cluster. It's the equivalent of a call, so it will, it's got high latency because it will do all that kind of replication stuff, it will make sure it's on disk, make sure you've got a quorum replying before the state machine changes, and only then will it return from the process command call. So that's a slow way, but the easy one to try. But then we got pipeline command as well, which allows you to send this equivalent of a cast. You send a command in, and then you could provide some options to get some asynchronous notification at some later point when that command has been applied to the state machine. So all the kind of consistency and replication magic has happened, you get a reply. So that's how you kind of achieve high throughput with Ra. And then we've got consistent query, which runs a query over the state machine. So this is the kind of strong linearizable query type. It requires consensus. At the moment it goes through the log. Soon it won't go through the log, so we'll have lower latency, but it will still be the slower of the query options. And then we've got local query, which allows you to query the local state of any of the members of our Ra cluster, which is obviously the fastest, but it can return stale results. So a write that you previously done, you may not be able to read if it's not the leader node or something like that. Right, so for the things that we're going to cover, the tools that we're going to cover today, there is a little repository, the Ra TOOLBOX repository in my GitHub account, which you can check out. If you're interested, I won't cover the entire code. Don't worry, we're not going to look at pages and pages of code. We're just going to cover the bits that hopefully will be interesting and worth discussing. Right, so the first tool that you do, it's kind of the one-on-one of the hello world, maybe, of replicated state machine. It's a key value store, right? It's a useful tool, but it's the simplest one. So in Ra, the key value store looks like this in terms of the Ra machine behavior implementation. So it's not a lot of code. We actually be able to fit all the code for it on a single, on a few lines. So in it, ignores the initial configuration map because there's nothing to configure, and it just returns an empty map. So it's a key value store, right? That's a good state machine, in-memory state machine state. Apply ignores the first argument. We're going to cover the argument a little bit later. The second argument is the command that you want to do, so a put command in the key value store, makes sense. The third argument is a state, so that's initially that will be your empty map. And then your return value is a tuple of 2 elements. We simply just the first element is just a new updated state, so that is our kind of state transition thing happening. We simply just put it into the state, and that's that. The second argument is the return or reply of the command. So if you're waiting synchronously using the process command, this will be returned in that, or asynchronously if you asked for an asynchronous notification. So that's all we need for a simple key value store. Although we might need to be just a little bit of glue around the client interaction. So in this instance, we use process command. We address one of the servers with a put command, and it returns a tuple of 3 elements. Okay, because eventually in this instance we hope it's successful. The result, so that's a second item in the reply return tuple here. So the okay, so it's okay. And the third element is the leader. So process command, if you happen to address a follower, because tracking the leader can't always be, it could change and you don't know about it. It will automatically redirect you to the leader and return the leader with your result, so that next time you can address what's hopefully still the leader and kind of gain a little bit of performance from that. Delete, same kind of thing there. Get, just make a lambda that queries the map that we've got in our state and returns it. Group membership. So for this, we would like to be able to, for processes, to join or leave named groups. We want crash processes to be automatically removed from the groups that they're in. So in Erlang, we detect crashes of processes by using monitors, right? But we can't just create a monitor inside apply, right? Because that will happen on all the nodes and it will be a different state, and it's a side effect. So we are going to cover how to handle that in RA. Erlang nodes can come and go, but are assumed to come back at some point. So we have a fixed topology here. They can crash, they can restart, they can be disconnected, but the assumption is that we don't have to kind of automatically detect when Erlang nodes might never come back, right? Although we could do that, but it's quite relatively unusual, I guess. Right, so here's code for that. Actually managed to cover most of that on one page as well. Again, it's a key value store. It's a map. The state is a map. We create an empty map. Any key, so we can have any name for a group. Doesn't matter. The group itself is effectively a set. I use a map here of PIDs with a default value, but it behaves like a set, right? So the state is a key to a set of key with a group name to a set of processes that are in the group. So join is relatively straightforward here. We just use maps update with to either create or update the group that the process wants to join. The next line 33, is more interesting, the effect. So we create something called a monitor process effect, and we return that as a third argument in the return value here of the state machine. So there's an optional argument to return an effect. So what are these effects? So the data that describes side effects that we want to have in the Erlang environment. So we use them to separate the state machine logic from the side effect that we want to have, right? So we effectively want to control the side effects, because if you restart, you don't want to reissue all the side effects again, because you only want them to happen, at most once. So in this instance, one way we can control the effects is that only the leader that runs the state machine actually actions them, and all the followers just ignore the effects that are returned as data, right? So that's one way that RA handles that. There's a variety of effects. So we can monitor processes or nodes. We can send messages to arbitrary PIDs that you know about. We can ask the leader to maintain a timer or call some arbitrary function. There's a few more effects. They're all documented at this link. But let's talk a little bit more about the monitor effect and how that actually works. So when we issue a monitor effect, we ask that the leader monitor this process on behalf of the state machine logic. And when the leader gets a down notification for this monitor, it will commit a command to the log. And the command looks like this. It's down, PID, and then it takes the info tuple from the down notification and puts that in there. And if you've ever used a monitor, which I'm sure you have, info is often the exit reason of the process, or it could be no proc if there was no process running with that for that PID at the time the monitor was requested. Or it could be no connection. And no connection is one of those, harmless looking PIDs that kind of embody everything that is hard about distributed systems. Because all no connection means is that the distributed Erlang TCP connection went down. It tells us nothing about the actual state of that PID that we were monitoring. It just tells us that it got disconnected. So we don't know anything. We don't know really what to do. Should it be in the group? Should it go from the group? What do? We can scream for a bit. And then when we finish screaming, we can see what we can actually do about it. So we know that Ra, the leader, will put an entry in the log, replicate it, and then it will be applied to the state machine. So we need to handle this new command that we didn't handle before we issued in the key value store, for example. So we need to handle this down command. So we handle the no connection case specifically. And what we simply do in the no connection says we can't reissue the monitor, as monitors are one-off triggers, right? So we can't reissue it because we'll just get another no connection because it's still not connected. The node is connected. We don't know. We can't communicate. So all we do is ask the leader to monitor the node, so it can tell us when it comes back up again. If it's not no connection, we simply just remove it from all the groups that the PID belongs to. So we know it's down. It's either doesn't exist or it has an exit reason, so it crashed, right? So it's gone. We can remove it. That's okay. Now that we issued this monitor node effect, we need to handle the node up and node down messages commands that will also be, appended to our log and replicated. So we need to handle them. And when the node comes back up that PID was on, all we do is we look at all the PIDs that we know about in our state and reissue monitor effects for them. So if that process crashed whilst we were disconnected, we're now reconnected, right? So now we can know stuff. If that process went down, we will now find out whether it went down. And if we don't get it down, then it's still there and should still be in the group. And then we handle node down as well, but we don't need to do anything for node downs because we already got monitors to handle the logic for that. There is one more case that we need to handle. What if the leader changes? What if the leader crashes or gets disconnected, right? If it gets disconnected, the followers will hold an election, or if it crashes or disconnects, they will hold an election and elect a new leader. This new leader doesn't know about the monitors, right? Because it threw away all the effects that it processed because it's a follower. It's just meant to calculate the state of the state machine. It doesn't do anything else. So we need to hook into the state transitions that happen inside the Ra process itself. And Ra is a gen statem, so it's actually quite simple to do. And in this case, we handle the case where the follower becomes a leader. And all we do then is just tell them, here are the monitor effects that we want the monitors that we want you to maintain. So that we just tell the new leader, monitor these PIDs. And if anything went down whilst the leader election happened, then we'll promptly know about it. Locks are useful. And we're talking about coarse grain locks here, like multi-second, multi-minute, leader election type, the kind of locks that you might take, if you want to have a leader amongst a set of processes. So there's a few ways to approach locks, and only some of them can ever be correct, but they have constraints, so we're going to cover a couple. So the first one we're going to talk about is it's a fencing token approach. The second one is the kind of session-based, where you kind of maintain a session, you got a lock, you kind of keep heart beating with the lock server in order to kind of maintain your lock. We are just going to use distributed Erlang sessions, right? Or combination of monitors, well, pretty much just monitors and timers in order to maintain a session. But it's roughly the same thing as doing an explicit kind of your own heart beating mechanism. And then there's a couple of approaches I will only mention, which are more leader election type of things that you can do, you can try out with Ra. So let's talk about the fencing token. So what is a fencing token? You might not be familiar with this. So a fencing token is a monotonic value that is provided with the lock. When you ask to acquire a lock and you're given the lock, you get a fencing token. This is monotonic, so every lock, every subsequent lock will have a high, the next value in the monotonic sequence. You usually lock around some resource as something that you're locking over, right? There's something you want to restrict access to something. This thing will need to be an active participant in this system for this approach. So the resource will need to reject requests from clients with a lower token than the highest it ever seen. I'm going to give an example. But in terms of Ra, all we need to do really is just use the index that comes with the log. Because the log is monotonic, the log inside Ra, we can just use that index as a fencing token. We don't even need to maintain our own state for it. We can just use that. Right, okay, so this is an example. Time goes from left to right. I didn't mark that, forgot. So the resource that we want to lock over is in green. The lock server itself is in pinkish. And then we've got two clients in bluish. Presumably we're all on different Erlang nodes. It doesn't really matter. This is an example. So from left to right, the client wants to acquire the lock. The lock is not held, so it's given the lock along with a fencing token of the number 55. The black line represents the time the client thinks it's got the lock. The client immediately makes a request, and that works perfectly fine. Client 2 also wants to acquire the lock because we want, fault tolerance. Like they all want to be available in case we want to be able to process the resource. So it requires a lock, but it doesn't get the lock because it's already held by client 1. So it just sits and waits for a notification that it's got the lock, asynchronous. At some point later, where the first little red cross is, the lock server gets one of those no connections. It's detected that it monitored, from client 1. That's not particularly clear there, but so it monitored client 1, it got the no connection. And immediately, because we're using a fencing token, it's able to just give the lock to client 2 who's waiting for the lock, but it gives it with a higher fencing token. And then client 2 immediately makes a request using the 56 fencing token, and that's successful with the resource. But client 1 still thinks it's got the lock, right? It hasn't detected the no connection on its side, right? Only the lock server detected it. The client hasn't done it. I don't know, it's blocking on something. TCP is being awkward. Whatever, it doesn't matter, it can happen. There's no guarantee that failures are going to be detected within any kind of particular timeframes. So it tries to make a request again, but the resource now it's seen a higher fencing token, so it rejects the request. And by that, the client knows, okay, I haven't got the lock anymore, so it kind of ends its presumed session. And some point later, it will detect the no connection, and it doesn't matter, and the client 2 is making progress. But you can see, I think you can see here, hopefully, how this is correct, right? The resource will only ever change by one client at a time. You won't get that interleaved. It won't allow interleaved invocations of the resource. I'm not going to go through the implementation. I'm sure you can imagine the implementation. It's not particularly difficult. The thing to note is here that the first argument is a map. It's a map of metadata around the log entry that's being applied, and it has the index in it, and we just grab the index and use that as the fencing token that we emit as part of our reply. The challenge here, the limitation, is that the resource needs to be, not all resources are able to actually firstly evaluate fencing tokens or maintain the fencing token state, which is kind of like a reliability problem in itself. So it's kind of just pushing the problem along a little bit. But if you can do this, this is the correct way to do locking. Session-based stuff. So we talked about time, right? So we have to use time for sessions, right? Timeouts. In our case, we're going to use the Erlang session, the TCP connection, the kind of the net tick heartbeats are happening as a implicit session. And we can use a timer effect to kind of set a timeout when we get a no connection and that kind of thing. It does have some severe downsides in terms of correctness. It does allow concurrent access to the resource or interleaved access to the resource. It will involve some degree of unavailability. So if you got potential lock holders, they might not get the lock for some time because you have to kind of give things a little bit of time to work. So let's look at some example for that. The upside is that it works with any resource, which is obviously very handy and very useful. Same setup. Client 1 wants to acquire the lock. It gets the lock. It doesn't get a fencing token this time. It just gets an OK. Client 2 also asks to require the lock. Sometime later, lock server gets a no connection from client 1. And it can't just immediately grant the lock to client 2 because it knows that client 1 might still think it's got the lock. So it starts a timer, the yellow bit, the yellow line is a timer, a grace period, whereby it won't grant another lock. And it needs to be long enough to give the client 1 a good enough chance to actually detect the no connection and voluntarily end its session. But you can never know, right? Because you disconnected. You don't know. But in this case, client 1 does eventually detect the no connection, the second red cross there, and it ends its session. But the grace period is still going, so no one holds the lock for a bit. That red line at the bottom, we don't like red lines. Red lines are bad. But eventually the grace period ends, or the timer triggers, and the lock is granted to client 2, and progress can resume. So this is a happy case scenario. This is fine. This is okay. A little bit of unavailability, but that happens as long as it works eventually. The other example is this kind of same setup, same detection of this no connection. Grace period is too short. Right? The grace period ends before the client 1 detects that it's disconnected from the lock server and should have ended its session. So client 2 makes a request, and then client 1 makes a request, and we got that interleaved access to the resource, which we want, which the whole point of a lock server is to avoid. You have to accept it. I mean, Erlang got some good tools, right? Soft real time, all those things. You can probably write a system that is, probability is high that it's going to be correct, but there's always going to be a chance that it's not going to be correct. With careful programming, you can do okay. Right, quite quickly now. One approach would be to follow the leader. So we've seen the state enter callback, the optional callback, where you can hook into the lifetime when a process becomes leader. Maybe you just spawn a companion process at that point. That could be the leader, and that can make progress. You still need to do a little bit of local heartbeating, but that's much different from doing heartbeating over the Erlang distribution, right? It's much more reliable. So you can have much shorter times of unavailability. You still have a small chance of concurrent access, but I think you could probably do a better job. Downside is that if you use this as a lock server that can hold multiple locks, all your leaders will be on one node, so you don't get any spread across your Erlang cluster. But there are ways you can get around that. If your problem is such that you can write it as a raw state machine, that would be a good way to do it. Still a small chance of concurrent access, but it's very, very small. But it can be difficult to write all systems as a pure function. So there are other tools that you could try out to write. Task queues, for example. There is an example in the Raft TOOLBOX repository of task queues, so you can check that out. Barriers, 2PC, whatever you want to do. They probably will follow very similar patterns in terms of failure detection. You need to know when these PIDs are gone. You need to know what happens. So you need to kind of detect failures and be able to deal with failures. So hopefully the other tools will guide you in that. So most of the tools, maybe not task queues, but most of the tools are like key value stores. So, the programmer in you would go, well, can we abstract? Can we generalize? Can we just have one tool? And it comes down to a choice ultimately. Do you want a toolbox or a multi-tool? In terms, looking at if you want to write a multi-tool, like one thing to rule them all, do take a look at this Zookeeper API. It kind of exposes a virtual file system, allows clients to create nodes. Those nodes might be ephemeral, so they're kind of linked to the kind of lifetime of the session that the client holds with the server. You can watch nodes, you can get kind of monitor-like notifications. You can have sequences to get fencing tokens. It's exposing all these simple primitives that you might be able to use to implement to implement these tools, although your client code typically will need to be more complex. So I kind of assumed I would end up with the Zookeeper API when I started this talk, but I actually ended up preferring the toolbox, having one state machine implementation for each tool that I want, and make that have exactly the semantics that I want it to have, rather than having kind of to use some tool with certain semantics. So it's a choice. I think it's a bit more Erlang to have a toolbox. Just me. Ra is designed to support many independent clusters, and that's a good point. You can spawn, thousands possibly of Ra clusters inside an Erlang cluster. So there is no performance. Sorry, there's no kind of performance reason to have a single thing. It's fine. You can have multiple things, multiple clusters. Right. So that's pretty much concludes the talk. I wanted to highlight another use of Ra than the RabbitMQ quorum queue. It's an experiment at this stage, but it's going really well. It's called mnevis. It's a replication layer for amnesia, so replicated distributed amnesia. I'm sure you never had any problems with distributed amnesia, but if you have, this implements the amnesia activity API for the replication layer. So it will have this Raft semantics. So you still need a quorum for things to work, but it might be a little bit less freaky outy when disconnections happen. It does break some of the rules for state machine implementations, but it's looking good.
I'm really curious about the quorum queue. What's the use case, or why would I use it?
Have you ever used RabbitMQ? Okay. So RabbitMQ has got an HAQ feature whereby you can have queue replication, right? So you got the queue and it's got servers on multiple Erlang nodes. It doesn't always work that well when you have things like network partitions happening, when your network isn't that reliable. It's also, when it's recovering, it can be a little bit problematic, queue syncing. So we've wanted to improve on it for a long time, and this is what we came up with, right? We thought we'd write it on top of Ra. We get quite simple semantics, yes. HAQs can shrink down to a single node and still work, so they have higher availability, but quorum queues will have better consistency and less, as long as you use publisher confirms, you shouldn't lose any messages that you have been confirmed. So it provides you with stronger guarantees at some price.
Why do you have a separate function for the consistent query one instead of using the process command, since that also allowed you to return a value?
Okay, so process command will always go through the log. So it will always be persisted onto the log and f-synced, right? None of the commands are applied until it's actually f-synced, so it's properly, as safe as the operating system allows you to be on disk. Right now, in the current version, consistent query also goes to the disk. So actually don't use it, but very shortly we will merge a pull request that avoids the disk completely but provides the same guarantees, and that's when you should be using it. Yeah.
Is state snapshot automatically done, or is it configurable?
I didn't cover snapshotting because limited time, right? But So there is actually an effect that affects the snapshotting. That is a bit of a special effect. Special effect, like a movie, yeah. It's called the release cursor. So you say, here is the state at this index. If you would like, kind RAS server, would you mind truncating the log at this point and replacing it with this snapshot? And the RAS server might do that for you. So I'll check the docs, or I can explain a little bit more detail on how it works later. But it's initiated by the state machine itself, right? The state machine needs to provide points at which, listen, it's a good time now. I know how many bytes I've got in memory. I know how many bytes I came in, maybe it's doing some calculation. You can say, now is a good point. Actually, the snapshot will be smaller than the log that you can delete. Thank you. Thank you very much.